All right, continuing with section 3-2. So we are up to an example of calculating standard deviation. So we're going to use the sample standard deviation formula to find the standard deviation of these Verizon data speed times. Okay, and we've done a few examples with this same little batch of data. Okay, so maybe before we do this, let me just show you that formula really quick. There are actually two of them, and I am going to use both. All right, so first I'm going to show you how to do it using this first formula, and then I'll show you how to do it using the second formula. Believe it or not, I know it doesn't look like it, but the second formula is actually a little simpler to use. Okay, all right. So the first step, if you're using the first formula, is to calculate the mean. So I have that there at the bottom. I added up all the numbers and divided by 5. And I think we had to calculate this same mean in a previous example. I think there might have been an example where it was just find the mean. Okay. So that's the first step. The next thing I'm going to do is I am going to subtract that mean from every single one of these numbers, and I'm going to put that in a new column where I write x minus x bar at the top. So let me try to be clear. So the way that I got these numbers was I went 38.5 minus 30.74, and that gave me this. 55.6 minus 30.74. 22.4 minus 30.74, et cetera, et cetera, et cetera. Okay. And a nice way to check your work after you've made this column is make sure that these numbers add up to 0. They should always add up to 0. If you do a little bit of rounding, I don't think I had to do any rounding in this problem. I think these are the way they came out. Then it might be just a little bit off, 0.01, 0.02, negative 0.01. But it should be really, really close to 0. And if you don't round at all, it should be exactly 0. Okay. All right. The next thing I'm going to do is square all of those numbers. And that is going to look like this. Okay. And again, I did not do any rounding. I guess it would be okay to round these numbers to 2 decimal places maybe. In general, you want to be careful about rounding because the more you round during a problem, the more it will throw off your final answer. Okay. All right, so the square of 7.76 is 60 point blah, blah, blah. The square of 24.86 is 618 point blah, blah, blah. Now, this is really, really important. None of these squared numbers in this third column should ever, ever be negative because the square of negative 8.34 is a positive number. So when you're putting that in the calculator, make sure that you put parentheses around this negative 8.34. All of these numbers should be positive. Maybe once in a while, some of them will be 0, but they should never, ever be negative. Okay, and then notice at the bottom of that third column, I have added up all of these squared numbers. Okay, when you add up all these numbers, you get 1,083 and some change. Okay. All right, so on the next slide, you're about to see the standard deviation formula again. And actually, I did something just a little different that I think makes a little more sense. Your book does something that I'm not too crazy about. They tell you what the standard deviation is before they tell you what the variance is. And I think that's backwards. Oh, okay. Well, you'll see me do it a little differently when I go over my practice problem. All right, so there's the mean. They rounded it to 1 decimal place. But I think they probably used the full value of 30.74 when they actually did the calculations. So this is the very last number that you saw at the bottom of the table. here's the formula. So this number on top of the fraction is that 1,083 and some change, and then you're dividing it by 1 less than the sample size. When you do a sample standard deviation, you have to divide by n minus 1, all right? Later on, we'll talk about population standard deviation. You divide by n instead of n minus 1. It's not a huge difference, okay? So 1,083 and some change divided by 4 comes out to 270 and some change. I do want to point out to you that this 270 number is called the variance, okay? And then to find the standard deviation, you take the square root of the variance. So the standard deviation comes out to 16.45 megabits per second. And notice that they've rounded it to 2 decimal places because the original data was 1 decimal place. So for standard deviation, just like for mean and for median, we round to 1 more decimal place than you had in the original data. Okay, so now let's talk about using the shortcut formula. So the great thing about the shortcut formula is you tend to run into not as many ugly decimals while you're doing it, and your table only has to have 2 columns, okay? So you start with your original data, and then you add those all together, just like you would do if you were starting to find the mean. Remember, the mean came from 153.7 divided by 5. Okay, but you don't actually have to find the mean. You just add those all together, and that's going to go in one place in the formula. And then over here, you just square your original numbers and add those together. Okay. So there are 2 important numbers here that are going to go into the shortcut formula. There's the sum of the original data, and then there's the sum of the squares. Okay. So here is the so-called shortcut formula. So the sum of the squares, that was the 5807 and some change. The sum of the original data, 153.7. So you do the sample size times the sum of the squares right here. And then you subtract the square of the sum of the x's and divide by n times n minus 1. So in this example, that's 5 times 5 minus 1. Okay. The 5,415.26 divided by 20, that's going to give you that 270 number, which is the variance. And then when you take the square root of the variance, you get the standard deviation. Okay, so now standard deviation is something that you really have to practice. So what I would like you to do right now, if you're watching the video, is to pause the video and try this problem. I would suggest try doing it using both formulas because that will really give you a feel for which one you like better. But then going forward, you can just use whichever one you like better. Okay. So listed below are the weights in pounds of 11 players randomly selected from the roster of the Seattle Seahawks when they won Super Bowl 48. And they want me to find the range, the variance, and the standard deviation. One little detail that I didn't include in this was they said, and also include the proper units. Okay, so see if you can remember how to write the units for the range, the variance, and the standard deviation. So go ahead and pause the video and try that, and then unpause it, and we will compare notes. All right, we're back. Time to compare notes. So the first thing to do that's really easy, as long as you remember to do it, is the range. So remember, the range is just the maximum minus the minimum. The round off rule for range, just like for standard deviation and everything else, or not everything, but most other things, is 1 more decimal place than was in the original data. So I would write that as 116.0 pounds. That's the range. Okay. All right, moving on to variance and standard deviation. So if you use the first formula, and I did this, well, I used Excel to make the table. I didn't really use all the bells and whistles in Excel. I just thought that would be a nice, neat way to present it. Okay, so here's my original data. Down here is the mean, 231.09. So then what I'm doing over here is subtracting the mean from each and every number. I forgot to check to see if those add up to 0, but I think they do. And then when you square all those, you get these numbers here. You add up all those squared numbers, they add up to 19,236.9 approximately. And then to get the variance, going up here for a second, the 19,236.9 is the sum of the squared deviations. You divide that by 1 less than the sample size, you get that the variance is 1,923.7 pounds squared. All right. So variance has those weird units. And then to get the standard deviation, you take the square root of the variance, and to 1 decimal place, the standard deviation is 43.9 pounds. All right, and then using the second formula, again, I think the second formula is a little nicer. So like in this one, you're not dealing with any decimals during the problem, you know, the part where you're making the table, okay? Not unless your original data has decimals. Okay. So the original data added up to 2,542. And then when you square all of the data, those add up to 606,670. So then looking up here, you can see where those things go. For the variance, you go 11 times 606,670 and then subtract 2,542 squared. And then divide that big number by n times n minus 1, which comes out to 110. And that miraculously gives you the same 1,923.7 that I got when I did it the other way. Again, that is in pounds squared. And then the standard deviation is just the square root of the variance, 43.9 pounds. All right, moving on. The range rule of thumb. That is I like how they describe this, a crude but simple tool for understanding and interpreting standard deviation. So with many distributions, the vast majority of sample values should lie with, with any distribution, the vast majority of sample values lie within 2 standard deviations of the mean. So for example, with certain distributions that are normal, remember we talked about the normally shaped distributions that are kind of bell-shaped and symmetrical. If you have a normal distribution, about 95% of your data will lie within 2 standard deviations of the mean. Okay? So let me explain to you what that means exactly. And we'll do that in a minute. Okay? So since the vast majority of your data is within 2 standard deviations of the mean, anything outside that range is going to be considered unusual, unusually high or unusually low. All right, so if something is more than 2 standard deviations above the mean, and that's what this symbol means right here. This is saying the mean plus 2 times the standard deviation. Anything that's bigger than that is significantly high. All right, the mean minus 2 times the standard deviation, anything that's less than that would be considered significantly low. Okay. And then anything that's within 2 standard deviations, they call it not significant. I'm not crazy about that term. It kind of makes it sound like it's not important. I would prefer if it said not unusual. Okay. All right. And if they don't have an example in here of what they mean by within 2 standard deviations, then I'm going to show you how that relates to the problem that we just did. Okay. All right. When you don't have the standard deviation, you know, maybe you don't have enough data to calculate it, and you just need a rough estimate of it. This is really interesting. You can estimate the standard deviation by taking the range divided by 4. The range divided by 4. That's a little gimmicky. All right. It's kind of hard to explain why that works. Gives you a very rough estimate of the standard deviation. Okay. We've been talking about this a little bit in the room just now. Can't remember if I said it on the video. When you're calculating standard deviation of a population, you use the same, this is a different version of the first formula. The only big difference is that you divide by n instead of dividing by n minus 1. And then remember, we talked about this a while back, the sort of tradition in statistics is you use Greek letters for parameters. Parameters are aspects of a population. So instead of using x bar for the mean, they're using mu. Instead of using s for the standard deviation, they're using sigma. Okay. And then the capital N stands for the population size. Okay. All right, so I skipped ahead a little bit, and I actually noticed that they did not have an example of what they mean by within 2 standard deviations, and I thought it was important to show that to you. So if you take the example that we just all worked on, in that example we found that the mean was 231.1. We found that the standard deviation was 43.9. So 2 standard deviations below would be the mean minus 2 times the standard deviation, and that would come out to 143.3. 2 standard deviations above would be the mean plus 2 times the standard deviation, and that came out to 318.9. So actually in this sample, every single one of those values is between 143.3 and 318.9. Every single one of them, 100%. All right. So yes, it would be unusual if any of the Seahawks players from Super Bowl 48 weighed less than 143.3 or more than 318.9. Okay. That would be considered unusual. Little bit of notation. I guess we've already talked about the variance. I personally think it makes more sense to talk about the variance before you talk about the standard deviation. I think the way they do it's a little backwards. So they're just pointing out here that the variance is the square of the standard deviation. So the reason I think it makes more sense to do the variance first is because, you know, you do the things, you add up the numbers, you evaluate that fraction, and that's your variance. And then you take the square root, and that's the standard deviation. So the way they're doing it is like evaluate the fraction, take the square root, that's the standard deviation, and now square it to get the variance. Take the square root and then square it. That's extra work. Talk about the variance first. All right. So the notation for variance, if it's a sample, you just write it as s squared. And if it's a population, you write it as sigma squared. Okay. All right. So there's all your notation: sample standard deviation, sample variance, and then population standard deviation, population variance. Properties of variance, already pointed out, the units of variance are the squares of the units of the original data values. So if your data is in pounds, your variance would be in square pounds. If your data is in megabits per second, your variance is in square megabits per second, whatever that means. The value of the variance can increase dramatically with the inclusion of outliers, which means it is not resistant. We talked about that term earlier in another video, I think. The value of the variance is never negative. It is 0 only when all of the data values are the same number. And that's pretty much never going to happen. The sample variance S squared is an unbiased estimator of the population variance sigma squared. And unless you're a math major, you really don't have to bother with that too much. Here they talk about why you divide by n minus 1 when you're working with a sample instead of dividing by n. So I'm not going to spend really a whole lot of time on that. That's another math major thing. This is worth pointing out, though, this second bullet. If you divide by n, sample variances tend to underestimate the value of the population variance. So when you divide by n minus 1 instead, it gives you a better estimate. All right, so really quick, we'll start talking about the empirical rule. We'll have to finish this in, I guess it's going to be part 3, right, of the video. The empirical rule states that when you have one of these bell-shaped normal distributions, the following properties apply. About 68% of all values fall within 1 standard deviation of the mean, about 68%. And you'll see again where that number comes from when we get about to chapter 6. Already mentioned a minute ago, about 95% of all values fall within 2 standard deviations of the mean. And about 99.7% of all values, as in like almost all of them, fall within 3 standard deviations of the mean. Okay. So what we're going to do next to kick off part 3 is we're going to use those numbers, the 68, 95, 99.7, and we're going to sort of get some additional information out of it that we can use to solve certain problems. Okay, so look for that at the beginning of part 3.